Let's look at a theorem now that is pretty easy to understand and accept, but uses the mean value theorem in its proof. So f is differentiable, and the derivative of f is 0 everywhere on an interval. Then f is a constant function. So basically we're saying if f prime is 0, then f must be a constant function. Now we know the other way around. We know that if the function is constant, it's a horizontal line, so the slope is always 0. But we're saying the other way, right? We're saying if we know the slope is 0 everywhere, then it must be a constant function to begin with. So the proof is fairly simple. And in order to prove this theorem, we're basically saying take two numbers in this interval, with, let's say, a is less than b. We want to show that the function is constant. So we want to show that however we choose the two numbers, the y values at these two x values are equal. F of a equals f of b. So this is what we're trying to do. So we're choosing a and b within the interval. So we know that f is continuous on the closed interval ab. Now f is differentiable. So if we were to choose this as my interval, so we're choosing a and b to be just two numbers in the interval. So since it's continuous throughout the interval, or differentiable throughout the interval, then it's continuous throughout the interval. So in particular, it's continuous on the closed interval AB, and of course f is differentiable on the open interval. So these are the two conditions for the mean value theorem. So the mean value theorem implies that f prime of c is equal to f of b minus f of a over b minus a for at least one number c. But since we know that the derivative is always 0, so even at this number c, the derivative must be 0. So in other words, we're saying 0 equals f of b minus f of a over b minus a, which basically means that the numerator must be 0. But if f of b minus f of a is 0, that means f of b equals f of a. So that's exactly what we wanted to show, so we're done with the proof. So any 2 points I pick in this interval, they're going to have the same y value, which means f is going to have the same y value everywhere on this interval. So here's an example where the mean value theorem helps us prove a basic result about a function. The next theorem is going to say that if two functions have the same derivative everywhere, so let's write that down. So f and g are two functions, and they have the same derivative. F prime of x equals g prime of x on an interval I. Then what this function is going to say is that the difference between these two functions is always a constant. Or in other words, one function is going to be the other function plus a constant. Okay? Now, let's draw a picture before we prove this theorem to see why it actually intuitively makes sense. Let me see this function. Oops. Here's a function f. Or I can call this function g. Let me call this g. Now if I'm going to draw another function f that has the same derivative everywhere as g does, okay, then it has to have the same shape so that the steepness of the graph is exactly the same everywhere. So for example, if I pick this x value here, this is the slope, same slope, and this is true at every point. And what the function is saying is, if this happens, then the difference between the functions is always going to be the same wherever I draw that difference. So if I draw it here, this number is c. They have the constant difference everywhere in the function. That's also c. So if two functions have the same derivative everywhere, then the only difference between them is that one is a constant. Another way to look at this is, for example, look at f of x equals x squared, and g of x is equal to x squared plus 8. What can you say about these two functions? What is f prime? F prime is 2x. And what is g prime? G prime is also 2x. So they have the same derivative, and so the difference between the two is just a constant. One is x squared, one is x squared plus 8. And of course, you know what these graphs look like. So one is a parabola with vertex at the origin. The other one is a congruent parabola. So this is g and this is f. And of course, this constant difference is 8. Okay? But let's see what the mean value theorem says about how to prove this. Well, actually, we can bypass the mean value theorem. The proof of this depends on the previous theorem. So let's say f and g have equal derivatives. So define a new function called h, and you want h to be the difference between f of x and g of x. Then if I take the derivative of this new function, h prime is f prime minus g prime. But because f prime and g prime are equal, h prime is equal to 0. And what did this previous theorem say about that? Whenever the derivative is 0, the function is a constant. So in this problem, h prime is always 0. Therefore, h of x is equal to a constant by the previous theorem. So in other words, take the definition of h from here. H of x, which is equal to f of x minus g of x, is just a constant. So in other words, f of x is g of x plus c. And that proves the theorem that if two functions have the same derivative everywhere, then their difference is just a constant. Okay? All right. Now for one last theorem. This theorem should be familiar to you. We used it earlier. We used it in trying to figure out where the function is increasing and decreasing. So suppose f is continuous on an interval I and differentiable on the interior of I. We don't care about the endpoints, in other words, for differentiability. If f prime if the derivative is always positive on this interval, or let's be more technically correct, on the interior of I, then f is increasing on this interval. And the other part of it is very similar. If the derivative is less than 0, is negative on all interior points of I, then f is decreasing on I. Okay, I'm just going to write a proof of the first one. So suppose f be as in the theorem and f prime is greater than 0. So let's choose, let a and b be two numbers in I with a less than b. The mean value theorem says f prime of c is equal to f of b minus f of a over b minus a. So if I multiply both sides by b minus a, I'm saying that f prime of c times b minus a is equal to f of b minus f of a. But this is always positive because that's what we're saying. The assumption is that the derivative is positive. Then a is less than b, so b minus a must be what? Also positive. And positive times positive is positive. So the right side must be positive. So in other words, f of b minus f of a must be positive, which in other words means that f of b is greater than f of a. All right? So up here, let's summarize what's going on. Here's the interval, and in the interval I picked two numbers, a and b, and I proved that f of b is higher than f of a. And this is true for any two numbers in the interval, which means that the function is increasing. That completes the proof. The part about decreasing is very similar. So in this lesson, we've looked at Rolle's theorem. We did not prove it. The proof is not too difficult. It's in the book. And we looked at how to verify Rolle's theorem with a specific example. For that, we looked at example number 12 in the book. Then we take a look at the mean value theorem, and we looked at an example from the book. This was number 21, how to verify that it works. And then we looked at a proof of the mean value theorem, which basically builds a new function that has the third property and use Rolle's theorem. Then we looked at three different theorems that use the mean value theorem in their proof. If the derivative is 0, then the function is a constant. If two functions have the same derivative, then their difference is a constant. And finally, the increasing decreasing stuff that we've been using. If f prime is positive on an interval, then f is increasing on that interval. So basically, none of the stuff that we were doing with graphing, optimization problems, none of that would have been possible without the mean value theorem. And so here you understand how the mean value theorem plays a crucial role in how to apply the derivatives, how to do the applications of derivatives.